So we're now going to begin quantum mechanics in 3 dimensions. So how is Schrodinger's equation modified when we go to 3 dimensions? Remember, our time-independent Schrodinger equation was H psi equals E psi. We already pulled out the time part. Remember, we already said the time was equal to e to the minus IE over h bar t. That still holds even in 3 dimensions. What did we have for h before? Before we had h as being the kinetic, but we were only in 1 dimension, so it was px squared all over 2m plus u of x. That was our Hamiltonian before. Now, in 3 dimensions, we're still only going to have 1 potential, but it's going to be a function of x, y, and z. But this other term here, to get the total amount of kinetic energy, we need to add up to get, so we need to add up all of the momentum. So it's px squared all over 2m plus py squared all over 2m plus pz squared all over 2m plus u, which is now a function of x, y, and z. Okay, we said, then when we did this, we said this was minus we said it was minus h bar squared all over 2m. And this gave me the second derivative with respect to x squared. But this is going to give me the same thing, but the second derivative with respect to y squared. So I can factor that out, plus the second derivative with respect to y squared, plus the second derivative with respect to z squared, plus u of x, y, z. So this is what the new Hamiltonian would be. Sometimes they give this a name right here. They call it the Laplacian. Or sometimes you might have seen it as, the gradient is partial with respect to x in the I plus partial with respect to y in the j plus partial with respect to z in the k. If you dotted this with itself, then you would just do put the i's together, the j's and the k's, and so this would be the second derivative with respect to x squared plus the second derivative with respect to y squared plus the second derivative with respect to z squared, or you could even write this as del squared right there. We wouldn't be a vector anymore because you dotted it with itself. So we could write this a little bit simpler as h is equal to minus h bar squared over 2m del squared plus u. But if we plus u of x, y, z. Or if we just come up to here and plug in, we get minus h bar squared over 2m del squared psi plus u, which is a function of x, y, z, psi equals e psi. So this is what the time independent Schrodinger equation would be like in 3 dimensions. Okay, so all it means is we have to, but I'll probably just use this one instead. This is the same thing as the del squared right there. It's called the Laplacian. So let's do it for a specific example. How about the infinite cubical box? Cubical box. Right here. So what is that? Well, we have some box here. Okay. And let's just make it simple. We'll say it's L by L by L. And we can say U is equal to 0 inside the box, inside. So we could say, maybe put the origin over here. So inside the box is really X is between 0 and L. X is between 0 and L. Y is between 0 and L. And Z is between 0 and L. And outside the box, U is infinite. U equals infinity elsewhere. Okay, so now the particle is free inside the box, but it has an infinite force on the walls. Okay, so how do we solve this? Well, we go back, and instead of plugging it in right here, I think I'll just use this second derivative right here in place of this right here. So this Schrodinger's equation is going to be minus h bar squared over 2m. And in place of that, I'm going to put the second derivative with the psi with respect to x squared. Second derivative of psi with respect to x squared plus the second derivative of psi with respect to y squared plus the second derivative psi with respect to z squared. Okay, plus u, which is a function of x, y, z, psi equals E psi. That's what we want to solve. Again, this is a partial differential equation. We'll solve it the same way we solved that partial differential equation last time. Remember, before when we had psi, big psi, and it was a function of x and t, we broke it up into little psi times the time. Well, on this one, we'll just turn this little psi into a function of x. Say x as a function of x, y as a function of y, and z as a function of z. So we'll break it up into the product of 3, and then hopefully we can turn our partial derivatives into total derivatives. Now, first of all, outside the box, out here, we already know what the wave function is. Just like the infinite well, psi outside of here, psi was equal to 0. Why? Because if we put an infinity into here, we're going to have problems with infinities over there unless psi is 0. Okay, so really all I care about is what's happening inside the box. But in the box, u is 0. So we can get rid of the u up there, make it a little simpler. We have no, that right there goes to 0 inside the box. Okay, so now if we plug this in, we get minus, what I think I'll do is I'll multiply everything by minus 2m over h bar squared. So this side over here becomes minus 2me over h bar squared, and I don't have this anymore right here. Okay, so what do I have? I have this term. If I wanted to do the second derivative of this with respect to x, I can pull out the y and the z, because they have no. So we can pull out the y sub y, z sub z, and then all I have inside there is x's, and that's the same as the total derivative, so we can make that the total derivative of x sub x with respect to x squared. And do the same thing with this one. Pull out the x and z plus x sub x, z sub z. And I get the second derivative of y, respect to y squared. And then the same with the z. We can pull out the x and the y, plus x sub x, y sub y, d squared z with respect to z squared. And on the other side, we multiplied this through, so it's minus 2m over h bar squared e times psi, which is x sub x, y sub y, z sub z. Okay, now I've gotten it down to total derivatives. Now the next thing we do is we divide everything by x sub x, y sub y, z sub z. So if we do that, then this right here, if we divide by this, we just get a 1 over x here. 1 over x sub x, d squared x sub x, dx squared, plus, if we divide by x, y, z, you just get a 1 over y, plus 1 over y sub y, d squared y, dy squared, plus 1 over z sub z, d squared z sub z with respect to z squared. And then over here, all of this is gone since we're dividing that all out. So that's just minus 2m e over h bar squared. Well, what do we have? We have some function of x. This has only got x's in it. This has only got y's in it. This has only got z's in it. And it has to equal that. Well, the only way this can possibly be true for all x's, you could hold x fixed and just vary y and z, and this equation should still hold. The only way this is going to hold for all x, all y, and all z is if this is a constant right here. This has to just be some constant. We'll just call it, say, alpha. Do I want to call it alpha or minus alpha? I think I'll call it alpha right there. Alpha could be negative. We'll just call this beta, some other constant, and we'll call this some other constant, but gamma. So we can see that alpha plus beta plus gamma equals this right here. Matter of fact, maybe I might even like it better with this h bar squared over 2m over here. It doesn't matter too much, but I think I like it better when I have the minus h bar squared. So I'm going to move it back. Minus h bar squared over 2m and make it that just e. That's just back to my e. I think I like that better. Okay, it's just that this is with each term. It's still the same, but now all of this is alpha. This times this is beta. This times that is gamma. Well, let's just look at this first term right here. We know that this has to equal alpha. So minus h bar squared over 2m, 1 over x sub x, d squared x sub x, dx squared is equal to alpha. Reason why I wanted to move this h bar squared over 2m back, because then it's going to be very much like our infinite well before. Because now, what we'll do is we'll now move the 2m over h bar squared, and we'll move the x sub x over on the other side, and so we end up with d squared x sub x dx squared. When we move the minus over, it's going to be a negative, but when we add it to both sides, it's going to be a positive. Plus 2m over h bar squared, alpha, x sub x, equals 0. This was exactly what we had for our one-dimensional infinite well. We had a psi, d squared psi dx squared plus 2me over h bar squared psi of x equals 0. It's exactly the same. What was the solution right here? Well, our x sub x ended up being a, some constant, a cosine, the square root of this, 2m alpha, all over h bar squared x plus b sine square root 2m alpha all over h bar squared x. Okay, and then how did we get our a's and alphas and so on? We looked at the boundary conditions. We said at x equals 0, psi has to be 0. And at x equal L, psi had to be 0, just like we did with the infinite well. So we can first say x sub 0 equals 0. Well, if we plug in 0, this is 1, so you just get a. That is 0. So a equals 0. So that means my x sub x is just b sine square root 2m alpha all over h bar squared x. And then what did we do last time? We said, well, x psi at L was also equal to 0. X sub L is 0 because you had to be continuous. X sub L was equal to 0, which gave me b sine square root 2m alpha all over h bar squared L. Well, the only way, remember we said b couldn't be 0. So the only way you could make this 0 is if this was n pi. So that means 2m alpha square root of 2m alpha over h bar squared L is equal to n pi, where we said n was 1, 2, 3, 4, and so on. Or my alpha is equal to n squared pi squared h bar squared all over 2ml squared. Exactly what we got for the energy eigenvalues before, but now it's just alpha. And then we took that alpha and we plugged it back in, and we got x sub x is equal to, and we, okay, I'll do it in 2 steps, b sine, it was n pi x over L. That's what I get when I plug my alpha right back into here. And then we normalized it to get b. Well, that's exactly what we did before. I don't even need to normalize it again. We know what it was. It was a square root of 2 over L. So x sub x is just the square root of 2 over L sine n pi x over L. Exactly what we got for the one-dimensional infinite well. That was for the x part. Then we have to, but now we've got to do it for this one right here. We have to solve this equation. Well, this equation looks the same as this, except instead of x's, we got y's, and instead of alphas, we got beta. So in that case, we're going to get beta is equal to n squared pi squared h bar squared all over 2ml squared. And we're going to get y sub y is equal to the same thing, the square root of 2 over L sine n pi y over L. And then we're going to get the same thing for z. It's the exact same. We're just going to plug it into here. Now, the only thing is, our x's, the n for the x isn't necessarily the same as the n for the y, so I should put in maybe a subscript. Maybe this should be nx right there, and nx right there, and ny, and ny. I don't know if, and nx right here. So that way, and then when we get to the third one, we'll just call it nz. So now we know what the psi is. We just have to multiply the three together. So that means my psi, it's going to depend on three quantum numbers now, nx, ny, and z. We're going to get y because you've got to get so many waves this way, and this way, right here. So we're going to get, it's going to be a function of nx, we'll call nx, and y and z. Those are the three quantum numbers of x, y, and z. And that's going to just be the product of x sub x, y sub y, and z sub z. So it looks like it's 2 over L to the, it's the square root of 2 over L cubed, or 2 over L to the 3 halves. That would be the normalization, and then you'd get the 3 sine functions. The sine of nx pi x over L, sine ny pi y over L, times the sine nz pi z over L. That would be the wave function, all the wave functions in this. Those would be the eigenfunctions, and then the eigen energy, the total energy, is just going to be alpha plus beta plus gamma. So it's just going to be this plus the one with the z. So my energy, which is again a function of the 3 quantum numbers, nx, ny, and z, is just going to be, I can factor out everything that's the same, pi squared h bar squared over 2ml squared. And then you'd have an nx squared plus ny plus nz. Nx squared plus ny squared plus nz squared. So there would be the eigenvalues. These would be the eigenfunctions. Again, they would all be orthonormal to each other. That is, if you plotted 2 of these right here that were different, integrated them with, then you're always going to get 0. And if you get 2 states with the same ends, then you get 1. So these are all the eigenfunctions. So if I wanted to get the general equation, whereas I don't know which one I'm in a combination of all of them, we would say psi is, I'd have to sum up all of the, it'd be a sum. I don't know if I should write it as 1 or 3 sums. I guess I could write it as 3 sums. You're summing up over nx equals 1 to infinity, and y goes from 1 to infinity, and z goes from 1 to infinity. And you'd have your coefficient, your alpha, nx, ny, nz, psi, nx, ny, nz. That would be your whole sum of terms right there. And remember, this term right here, if you would have just, what this term is the probability amplitude of measuring a particular psi. So if we said something like alpha, say 1, 1, 1, when x is 1, nx, and y is 1, this right here is the probability amplitude of measuring psi 1, 1, 1. Or this squared would be the probability of measuring psi 1, 1, 1. Okay, if I wanted to say, and now again, if you want to know what these things look like right here, remember, if we wanted to know what just the 1, 1, 1 state would be, that would be, it's kind of hard to draw something in 3D, but along this axis, remember the sign, the first one was just a bump like that, and then you'd have a bump that kind of looks like this, and then you'd have another bump that kind of looks like this. So if you bring them all in, it looks like it's almost a cloud right in the middle of it, right there, and it dies out at the two ends. It's kind of hard to draw that right there. If you wanted to know what the second state looked like, let's say the 222, 222 would have two bumps. The probability would be like two bumps here, and two bumps here, and two bumps there. And so it'd be a bunch of, I don't know how many blobs you'd have. I guess you'd have 8 blobs or something, you know. 4 of them in the top and 4 down below, right there. You'd have some, and you could have even said 2, 1, 2, you know, and some of them you just have a single one, and the other ones you'd have 2 blobs. But again, it's a 3-dimensional one. I can't quite view it here, but that's all you're doing is you're just adding waves from the 3 different directions. Okay, what if I asked, what is the probability that you'd find the particle, let's say between, how about between, x goes between 0 and L over 2, probability of finding the particle between, let's say, x is somewhere between 0 and L over 2. How about y is somewhere between 0 and L over 4? And how about z is somewhere between L over 2 and, well, let's say 2/3 L, z, and L. Suppose you ask, what is the probability of finding the particle? So over here in my picture, I don't know which is x is, but you could say x is between 0 and L, and then you have a certain y and z, and so you'd have a little bit of a rectangular cubical box in there. If you wanted to find the probability that you're in there, all you have to do is you just have to integrate psi star psi. We just have to integrate psi. If we want to do it for a specific state, but for in general, we could just say nx, ny, nz, star, psi, nx, ny, nz. Remember, that's the probability where you'd find it at a particular value of x, y, and z. And if I just wanted to integrate that over, I have to integrate 3 times because you have it over x and y and z. So if you just put a dx here, it'd be from 0 to L over 2. If you put a dy there, it would be from 0 to L over 4. And dz here, it'd be 2/3 L to L. Okay, dx. Okay, sorry, I did that. Sorry, doesn't equal 1. That would be the probability. That would be the probability. If I said from 0 to L, 0 to L, 0 to L, then you'd get 1 right there, because then you'd be normalizing it. Okay, so this would be the probability. Now, suppose we look at the energies here. If we look at, let me call this, for just to make it easy, I'm going to call this E naught, E sub 0. It's h bar squared, pi squared over 2ml squared. And so if we look at let's just say for nx, ny, and nz, these could be different quantum numbers. The lowest state for all of them is 1, so the lowest state of the whole system would be a 1, 1, 1. And then we could say, what's the energy? Well, you'd get this E naught, but then you'd have 1 squared plus 1 squared plus 1 squared, which would just be 3. 3 E naught. So the energy would be 3 of those E naughts. If we wanted to know what the wave function was, you would just plug in 1, 1, 1 into here. So you would just plug in sine pi x over L, sine pi y over L, sine pi z over L. That would be the 1, 1, 1 state. The next state up would be, one of these could be in 2, let's say 2, 1, 1. Well, if we come up to here, if this is 2, so you got 4 plus 1 squared plus 1 squared, that's 6 E naught. So this would be 6 E naught, and that would be the wave function. You'd put a 2 in there, you'd put a 1 in there, and you'd put a 1 in there. If we look at 1, 2, 1, well, if I make this 1 squared plus 2 squared plus 1 squared, it's still 6 E naught. And you just plug in a 1, a 2, and a 1. If we look at 1, 1, 2, well, that's going to be still exactly the same. 1 squared plus 1 squared plus 2 squared is still 6 E naught. If we look at the next one, the next one up would be 1, 1, is it 1, 1, 3 or 2, 2, 1? 1, 1, 3, that would give you 1 squared plus 1 squared plus 3 squared. That would be 11 E naught. What about 2, 2, 1? That would be 4 plus 4, 8, 9. So it looks like 2, 2, 1 is smaller. So 2, 2, 1 would be 9 E naught. And then you could do, say, 2, 1, 2. That's another 9 E naught. Or I could put 1, 2, 2. It's 9 E naught. And so on the next one, I guess we could put is 3. There'd be 3, 1, 1. We said that was 11 E naught. And so on. Then there'd be 1, 3, 1 and 1, 1, 3. Now, you'll notice that there are 3 states here that give the same energy. We give a name to that when multiple eigenvalues give you the same result. They have different eigenfunctions. They're different. One's 2, 1, 1, one's 1, 2, 1, and one's 1, 1, 2. But they give you the same value. We call this degeneracy. Degeneracy. So we say the degeneracy of this state, right, this energy is 3. So we would say a degeneracy is 3. We would have said the degeneracy of this one is 3. Degeneracy we never had degeneracy in one-dimensional wells, but in three-dimensional wells, we can now start to get degeneracy. Why is that important? Well, remember, when you measure the energy, it collapses the wave function. The only thing is, what does it collapse it to? Because normally, there's a 1-to-1 for each psi, there's a particular energy. But now we have 3 energies. We don't know which one of those 3 it is. So if I were to have found 6 E naught here, and I say, what's the state, what does it collapse to? Well, that state now would collapse to alpha. So what do we say? Measure 6 E naught. So you could say collapse to state alpha psi 2, 1, 2, 1, 1, 2, 1, 1, plus some beta psi 1, 2, 1, plus some other function, alpha gamma psi 1, 1, 2. So I don't get to bring it down to the exact wave function that I want. I can only bring it down to a multiple of these 3 right here. So I need to, if I wanted to just get the exact wave function at its end, I have to do something to whittle this down even more. Now, one way you could whittle this thing down a little bit more is, the reason why you get degeneracy is because of the symmetry. A box has a lot of symmetry to it, especially a cubical box. You notice here, if I rotate it 90 degrees, pretty much any direction, it looks exactly the same. So there is a lot of symmetry in here. Anytime you get symmetry, you're going to get degeneracy. And when we look at something like the hydrogen atom, which is like a sphere, there's a lot of degeneracy and a lot of symmetry in a sphere. So one way you can break this so that you don't have degeneracy is don't make it a cubical box right here. You know, what if the box was longer and skinnier right here? You know, something like that right there. Well, you don't even want any of the dimensions to be the same. You don't even want them to be multiples of each other. But if they were all like irrational numbers, their sizes, their lengths, then you could get rid of all the degeneracy. Or you could break the symmetry by putting in some sort of a magnetic field. If you put a magnetic field in there, then you're getting rid of any sort of symmetry all the way around. Or an electric field. You put a magnetic field or an electric field in there. You'll notice if the box was it wasn't a cubical box, but it had dimensions, let's say Lx, Ly, and Lz, then what would the energy be? I couldn't factor out the L's because it wouldn't all be the same, and you would have had the energy is equal to pi squared h bar squared all over 2m, and then you'd have to say nx squared over Lx squared plus ny squared over Ly squared plus nz squared over Lz squared. And as long as these didn't give give the same energy for multiple different ends, then you wouldn't have any degeneracy. But this would be the energy if it wasn't cubical. Okay, so the only problem with all this is most things in nature aren't cubical. Most things in nature are spherical. And most potentials are not, you know, you'd hate to put them in rectangular coordinates because most of them just depend on the radius, like gravity or the electric potential. You know, so you know, whenever you have a sphere, you know, U is just going to be a function of R. And so the last thing you want to use when you've got spherical symmetry is rectangular coordinates. So on the next lecture, we're going to show how we do this in spherical coordinates, because doing it in working out spherical stuff in rectangular coordinates would be a mess. It's already going to be quite a bit in spherical coordinates, but it still makes it much easier. Okay.